I'm Tim Ventura, and we're joined today by Josh Storrs Hall, award-winning subject matter expert, thought leader, and influencer in the field of molecular nanotechnology. Josh is the author of Nanofuture, What's Next for Nanotechnology, a fellow of the Molecular Engineering Research Institute, research fellow at the Institute for Molecular Manufacturing, founding chief scientist at NanoRex, and former president of the Foresight Institute. Josh is an editor of the Technology Roadmap for Artificial General Intelligence, associate editor for the International Journal of Nanotechnology and Molecular Computation, and contributor to the Technology Roadmap for Productive Nanosystems. He was awarded the 2007 Bella Cornitzer Prize for Nanofuture, the 2006 Foresight Nanotech Institute Communications Prize for Nanofuture, and is the originator of Nanotech Smart Dust and Utility Fog. So Josh, welcome. A while back, we discussed nanotech extraction of uranium from seawater for nuclear power, which you described in your book, Where is My Flying Car? So I wanted to explore that concept a little more today. But before we get into that, let me start by asking what the current state of nanotech research is. What are the most interesting advances taking place right now?
Hi, Tim. Happy to be here again. What's actually going on in nanotechnology right now is that mostly it's in the area of what I would call enhanced macromolecular biology. It's people are beginning to be able to use the mechanisms inside cells that make all the pieces of cells and make them work and so forth, to do things that cells don't naturally do, and are beginning to move out in the direction of actually inventing new stuff at the molecular level that they can use these tools to build. I'll say that the other main thing is that 3D printing is getting more and more precise and is getting close to something we might consider, if not molecular, at least microscopic scale devices that can be made. And when you get those two capabilities together, there will probably be a synergy and a synthesis that is more than the sum of its parts.
Well, and actually that touches on a couple of my later questions. So we are right on target. But let me first ask, so producing nanoscale materials with traditional manufacturing is becoming more common, but the key to molecular nanotech has been self-replicating nanoassemblers, right? And I'm wondering, we haven't created these yet, from what I understand. Yeah. But would it be fair to say that life on Earth and cellular biology is proof that these are possible?
Oh yeah, of course. The cell is a self-reproducing machine, and it goes to make up everything you can see if you look out the window, and everything you eat, and produces all the oxygen you breathe. So yes, I mean the life is a big fact, and we're just saying, well, we can do that too. And as I was sort of hinting at before, we're beginning to understand enough about how life does it that we can sort of just hitch up to it. And this is of the two basic paths that were laid out towards nanotechnology. One was laid out by Eric Drexler, and this is the one that's happening right now. The other one was laid out by Richard Feynman, and I've been a champion of that particular line of development, but mostly because everybody was doing the other one, and I figured this needed a helpful push as well. It's not going as fast as the biologically based research, but it's still sitting there and it's waiting. And as you can see with the constant improvement in things like 3D printing, it looks like that it's not unlikely to contribute to the ultimate shape of the technology when we get it.
Yeah. Well, and again, the reason that I kind of touched on that is skeptics would point out that biology is natural, right? It evolved, and nanotechnology is artificial, it's engineered. But that line does seem to be blurring. In my case, I'd read about something called Hatchimoji DNA. I'm probably mispronouncing that, which is a synthetic nucleotide acid analog with applications for data storage and possible insights into the evolution of extraterrestrial life. So in this case, basically what you're talking about is like DNA strand, except that the nucleotides in it aren't the four normal base pairs. If I remember correctly, they added new base pairs and then it incorporates the traditional base pairs as well. And so again, this is something that is engineered. They're looking at being able to use this for data storage, and obviously, there are insights into how life evolved and how it works, right? So we've taken something that's natural and made it artificial and basically engineered for like a purpose, I guess. And it seems like that's blurring the line.
Well, I would put it slightly differently. I'd say, look, a horse is natural and a buggy is artificial, and yet they work together perfectly well. And we've used them for centuries. And so we're in a new horse and buggy era where the horses are the natural molecular processes in cells, and the buggies are things like the Hachimoji DNA, which is basically you go and you put a harness on the horse and use it to pull your buggy, and there's no reason to imagine that these two things are antithetical. In fact, they're the opposite, that they complement each other and form the basis of a very useful technology.
Yeah. Well, another approach that some nanotech researchers are taking is bypassing the nanoassembler challenge entirely and experimenting, as you mentioned, with concepts from 3D printing and semiconductor fabrication to work on nanoscale products now. And I think the assumption there is, if we can start to develop these novel compounds, again, these engineered, intentional nanoscale technologies, that we can basically use nano assemblers to enhance those in the future. Does that seem like kind of a viable short-term path to engineering at this level?
Well, I think that people don't understand just how much of a holy grail pure nanotechnology assemblers, or essentially a molecular based uh, technology base is, compared to all the other stuff that we're doing now. It's just so much more capable that it's basically, it's just a shame that people aren't pushing towards it more directly than they are. But I think once they get there, all of a sudden everybody's going to realize it. And it's going to be kind of like what happened in artificial intelligence over the past couple of years. All of a sudden, everybody suddenly realized, my God, this stuff actually works. And the amount of money pouring into AI right now is phenomenal. Okay. Uh, Sometime in the next 5 years, at my best guess, the same thing is going to happen in nanotechnology. And then we'll be off to the races.
Yeah, yeah. It makes sense. I look at all of these things as kind of a progression, right? And you have to do the groundwork for the pieces before the next step can be taken. And it seems like the groundwork is still being taken with nanotech, but I'm still seeing headlines. I'm still seeing like novel approaches and compounds being developed, right? And so once it reaches kind of that critical mass, right? That's, I think, what we're seeing with quantum computing, where people start to say, wow, you know what, this actually works, and then the money starts to pour into it and you have this explosion of development.
Yeah, well, part of the problem is, and for someone who spends a lot of time observing developing technology, this is probably one of the worst problems, is that you have a few people who have a vision of what a technology could be, like the artificial intelligence researchers as far back as the 50s. Okay. And Feynman with the nanotechnology, and Drexler, and so forth. And they put this stuff out and they put a word on it like artificial intelligence or nanotechnology. And everybody falls in love with the word and say, wow, this is going to be great stuff. And they start applying that word to what they're doing, which is not what the vision actually was. Okay, so you get a lot of stuff that was called artificial intelligence, back in the 80s and the 90s and the aughts. You get video games that said artificial intelligence, and it was like the little algorithm that ran the non-player character. And yet there was a real thing there. There was a real artificial intelligence that could be gotten to and has almost gotten to right now. We're not really what I would call AI, but we're getting darn close. And so the same thing is true with nanotechnology. There's a lot of stuff out there that calls itself nanotech. And so it makes it really hard for an observer of progressing technology to understand when the watershed is actually reached. And yet, that's our job. We're, and so we have to just get out there and do it and say, okay, this isn't it yet. This isn't it yet. This isn't it yet. Hold your breath. That's it. And so that's going to happen, within the next decade, I think, both for true AI and for nanotechnology.
Yeah. Yeah. Well, let's dig into seawater extraction. This is the thing that I got really excited about.
Metaphorically.
Yeah. Well, I guess metaphorically, so we'd have to scoop into seawater extraction, right? So you have written that there are over 4 billion tons of uranium dissolved in the Earth's oceans, which works out to 100 quadrillion watt hours of energy. That's enough to supply the current American 10 kilowatt level of power to 10 billion people for 10,000 years. So instead of mining that on land, we can leverage nanotech to pull that out of the ocean, right?
This is true. The thing is that, we actually have the technology to pull uranium out of seawater right now without going to flat out nanotechnology. Because all it really takes is a certain amount of material science where you can produce a material, basically just strings, that have receptor sites on the surface that will bind to the dissolved uranium in the seawater, preferentially to something else. And so you just make a huge mat or skein of these strings, and you throw them in the water and you leave them for a while and you pull them all out, and there's lots of uranium that you can then wash off of them and throw them back in again. And that's a fairly broad brand of technology. You can do that for a lot of stuff that's dissolved in seawater. The trick, and the key trick, is how expensive is it compared to other ways of getting the stuff. Well, it turns out that for uranium, it's still 5 to 10 times as expensive to use the extraction techniques we know than to just have it, dig it out of the ground and refine it. And so the main problem for seawater extraction of uranium right now is that uranium is too cheap already. And when I say too cheap as opposed to the extraction is too expensive, what I mean is that if we needed to power the world on extracted seawater uranium, we could do it. It's not too expensive to be used for our primary energy supply if that was the only way to do it. But right now, it's even cheaper. Real uranium, when I say real uranium, stuff coming out of the ground by conventional mining techniques and processed by conventional processing techniques. So yes, it's there. And yes, we're going to find more and more inexpensive and efficient ways of getting it. But right now, uranium is so cheap. The question doesn't even arise. We should just start using uranium. We need to be using about 100 times as much uranium as we are now, and that's because we need to take the proportion of electric power that we use now and make it all nuclear,
Mm.
simply because it's just so much of a cleaner way of producing power. And the other thing is, and I'm talking about, say, people in the United States, right? And the other half of that factor is that there are lots of people in the world who just don't have anywhere near as much power as we do, and they need it. And they need it to attain a what we would call reasonable level of standard of living. And so we need to push uh, our capability of not only producing uranium, but of harnessing it and providing people with clean power, um, to the point that everybody says, "Oh, I'm trying to help the poor." Well, if you want to help the poor, create nuclear reactors.
Yeah. Well, uranium isn't the only material dissolved in seawater. And so I did a little bit of research last night. I just looked up a couple of, common chemicals that came to mind. One of them was lithium. That's critical for smartphone and electric vehicle batteries. Now, the open access journal Joule says that while there are 43.6 million tons of lithium in land-based sources, there are over 5,000 times that amount dissolved in seawater. But the gotcha is the concentrations are 0.18 parts per million, right? So I think we'll find that with a lot of these rare materials. Lithium is one example. I know there are questions about mining. There are questions about pollution related to mining as well. But, like rare earths, right? That is something that the US is in contention with China about. That would also apply. Those rare earths are dissolved in seawater, but at very low concentrations. So by using nanotech and processes like that, potentially in the future, we could solve those land-based mining issues, right? By just literally pulling them out of the water.
Yes, although let me kind of weigh in here with if if you want to start using uh, nanotechnology to mine seawater, um, you're kind of doing something like saying 200 years ago, let's develop the internal combustion engine because it would make it easier for us to get hay for our horses. Um, and the fact is, it does. It makes it much easier to get hay for our horses. But what it's done is replace the horses. And so the fact that we need a lot of lithium for batteries is an odd coincidence of our current technology that we don't have better batteries and that use other things. And in fact, if we had flat out good, useful, working nanotechnology, we wouldn't need batteries at all. We would have fuel cells that ran completely cleanly and didn't have anything like the limitations that chemical batteries have. In fact, we might even, if we would to do a lot of actual science and work on this stuff, we could probably have nuclear batteries, um, and then you wouldn't ever need recharging or refueling. So the thing is that yes, it would help, but even more so if we do get to nanotechnology, a lot of the so-called problems just vanish because the nanotech has direct applications to the end results, the end products, and the end processes, as opposed to the current needs of the current processes, which are just stopgap gaps because that's all we know how to do right now.
Yeah. Well, and again, I just grabbed a couple. Another one was platinum. Mining.com ran an article saying there's $16 trillion of platinum that could be extracted from seawater. They estimated over 300,000 tons is dissolved in the world's oceans. And one of the things you had mentioned this in your book, again, that's Where is My Flying Car? And it's available on Amazon. I'll put links in the show notes to that. A lot of these are they're bound up in ocean rocks, and there's a homeostatic equilibrium that's involved. And so, like in the case of uranium, when you extract this from seawater, if you have a large long-term operation, that homeostatic equilibrium would change slightly, but it's going to naturally basically pull it out of that bound state in rocks, right? So, in a sense, that supply doesn't just run out. You may thin it out in a certain
Yeah,
area, but it's going to naturally restore balance
yeah,
over time.
yeah. The best model I found for thinking about that is that the uranium in the seawater is like your wallet, and the uranium in the seabed minerals is like your bank account. Um, and so when you run low on your wallet, it comes out of the bank account, or even better, it's like your job. It just keeps coming in at some appropriate rate. Um, and so yeah, so the bottom line is that there is way the hell more uranium out there um, than we currently have any clue what to do with. Um, on the other hand, because it is actually out there in the seabed minerals, um, another option, should we suddenly decide, we get into a war with Alpha Centauri or something, and we just need huge amounts of power, you just go dig it up in the seabed. I mean, there it is. Um, and that's something that I expect to happen over the next century as we get better and better robots and um, are able to go out there and just extract all the stuff directly without waiting for it to sort of leach slowly back out into the seawater. Um, and there's all sorts of other really great reasons for wanting to do that. I mean, if sea levels rise, um, all we have to do is go out there and mine the seabeds for energy and use the energy to mine the seabeds for dirt and build mountains and islands and stuff like that and create more room for the seawater to sit in. I mean, we are actually capable or getting close to being capable of doing projects at that scale on this planet. Um, and, and and people without an understanding of the immense uh, potentiality and capabilities of nanotechnology have a hard time understanding that. But as far as I understand the technology and the physics and our capabilities and the ultimate power of a self-replicating technology, um, it's real. I mean, that's something that we could be doing by the end of the century.
Well, and as you said at the beginning of the interview, look outside of your window, you see the power of nanotechnology, right? And that's
Yes.
biological, it's evolved, it's natural, but it has changed the face of the earth. So there are a
Mhm.
lot of advantages with seawater extraction compared with traditional mining. I wanted to get into some of these
Yeah.
just briefly, but I mean, it
Yeah.
lets us avoid the infrastructure that's involved with
Mm.
land-based resource location, excavation, mining, material separation, and waste product disposal, right? So
Yeah,
again,
well, it's different. It's different. Right now, we actually more than half of our magnesium comes from seawater. Okay. Now it happens to be one of the more common dissolved elements in seawater after salt. But the like I say, more than half of the magnesium you use comes from seawater. Um, and so if you want to know what this would kind of be like, you look at how the magnesium plants work. They basically, they build a plant on the seashore and they run these pipes way out into the ocean because you need the water to be moving around and replenishing the water from the stuff where it's depleted. Um, and then they have big pumps and they pump the water through and uh, I mean, the Nazis tried to use filters on ships to extract gold from seawater, uh, unsuccessfully. Let me point out, but um, depending on what the other part of your technology is doing, the amount of stuff that you're pulling out of the seawater, anywhere you have a flow of seawater, if, for example, I mean, by far the most common part of seawater that people need to use is water. And as populations rise and technology improves and so forth, more and more of drinking water and fertilizing water is going to come out of the ocean by And whenever you do that, you may as well take the uranium and all the other stuff out too. Um, there's a decent chance that by the end of the century, for example, people will have these big pipelines where they ship the water all over the country just for use as water, but they'll also be taking the minerals out, and that's completely feasible with
Yeah.
especially with any kind of a close to nanotech industrial base.
Well, and this, I mean, this only gets better because basically what we're talking about is a materials soup, right? And so, in
Yeah.
addition to minerals, seawater is filled with organic materials such as fatty acids, aromatic and aliphatic compounds, alcohols, and much more. There was a study that I found last night that said a lot of that just comes from phytoplankton, right? So, these just,
Oh yeah.
these are
Well,
naturally occurring and they're in the ocean now, from a nanotech perspective, though, you could harvest these and use them as a shortcut to build up complex compounds that we use in a range of products.
the biggest animals on Earth, the baleen whales, work that way. They pull material out of the seawater by passing it through filters, and boom, there they are. So it's clearly possible. The only question is the same one as we talked about before. What's the optimal? What's the least cost? What's the most easily achieved way of doing these things? And there are many different ways. So while that I think is in fact feasible, I don't know how to compare it right now. I have no idea how to compare it to the other feasible ways of getting the same materials.
Yeah. Well, in addition to that, I also wanted to mention that in 2013, researchers from Aberdeen University announced starting a hunt for undiscovered chemicals in organisms that evolved in deep sea trenches. And so, in their case, they were looking to find like next generation antibiotics. I think they started in the Atacama Trench as well as trenches off New Zealand in Antarctica. So, in addition to extracting elements and compounds from seawater, we could use it for drug discovery as well. So there's just such an amazing range, right? And nanotech is like an enabling technology here, especially when you get into things on that level, right? Because like as you mentioned, magnesium, we can pull that out in bulk. Salt, I mean, everybody knows that's pulled out in bulk, right? But when you get into separation of these more rare or novel compounds, uh, I believe nanotech is probably a really powerful enabling tool there, right?
Oh yeah, yeah. Actually, I love the way you use the word range. Have you ever read the book The Deep Range by Arthur C. Clarke? Is one of the great. He was of all of the classic science fiction writers. He was the one who was. I mean, many of the guys were flyers and into rockets and stuff like that. He was a diver, and so a lot of his science fiction uh, dealt with the uses of the ocean. Um, and he was a firm believer that after another century or so, the oceans were going to be the uh, the new breadbasket of the world, and that and I can't argue with him. I think you're completely right that there's so much stuff to be found in the oceans, and that we will use the oceans as uh, a major resource, um, and we'll all be better for it.
Yeah. Well, I want to jump off the speculative cliff now, so to speak. So
Whee!
I've been following the UAP phenomena lately, and one of the things that I've wondered, is we're seeing all these reports of these Tic Tac UAP, and a lot of people are saying, they have to be extraterrestrial. And I thought, if that's the case, maybe these are some kind of nanotech self-replicating von Neumann probes. And again, this is highly speculative, but if that turned out to be the case, do you think seawater extraction could explain why these things are being encountered in the ocean?
Well, I have a yes and a no for you on that one. I think that if we do see something of extraterrestrial origin of a technological nature, by far the most likely thing we're going to see is a von Neumann probe. That's going to be something that's made to be thrown out in tiny pieces like an insect egg or something, and just or the down of a thistle. I mean, come on, the most successful forms of replicating life and so forth work that way. And so by far the most likely thing we're going to see is some kind of a von Neumann probe. Now, exactly what it's going to be, I have little idea. I mean, I think the oceans are more interesting to us because we're here and we're stuck in this gravity well, and it's easy to get to, and there it is, and we're learning how to use it. But we've lived off the oceans for as long as we've had reading and writing. I mean, the so this is something that is a good thing for us. But if I were a probe in outer space looking for a place to land and build copies of myself, the Earth is probably not what you're going to expect because we're a fairly rare planet. And there's lots of reasons why almost all the planets in the galaxy are not like the Earth. And you can buy books about it, about just how rare a planet the Earth is. So if somebody is designing a von Neumann probe to hit the average planet, it's not going to be designed for the Earth. Now, whether or not it's going to be smart enough to adapt itself to the Earth is a completely different question. But that's what I'm going to leave to the Antarians or whatever they are.
Yeah. Well, and I want to flip this around again. Another highly speculative question is whether NASA could use this principle on our own space program. There are salt brines on Mars, Saturn's moons and Jupiter's moons both have liquid oceans capped with ice. So rather than trying to mine and refine resources on these planets, could future probes extract critical fuel, energy, or other chemicals from their oceans? And again, the idea is to eliminate that infrastructure, right? Because in the case of our own exploration, we can't easily build that. I mean, weight is a critical issue. Being able to transport that halfway across the solar system is a critical issue. If we want to build anything on the surface, in situ resource utilization is key, right? So, would it be preferential, I guess, to be able to leverage that concept?
I think for a first shot, it's worth a try. I think if NASA wants to try and do von Neumann probes itself, and we know enough about these moons to do that. I mean, there's basically two sort of oceans that we can go into. One of these subterranean oceans that are kind of like ours. They're liquid water and probably have dissolved minerals in them and all that sort of stuff. The other thing is that the atmospheres of the giant planets themselves, or even of Venus, there's a lot of stuff in those atmospheres, and we've actually sent probes to all of them, and we actually have good ideas of what's there. So if you just take a good big step backwards and you look at a planet and say, well, there's a big ocean on this planet. It just happens to be gaseous rather than liquid. I think we'll find that both of those are excellent chances. We need to come up with designs. We need to try them out. We need to try them out again after they fail. We need to try them out again after they fail again. But ultimately, we'll find that we're going to be able to put self-replicating technology in atmospheres and oceans.
Well, and I think Arthur C. Clarke alluded to that in 2010, right, with the monoliths over Jupiter.
Absolutely. Yep, absolutely.
But Josh, thank you so much for your time today. It was wonderful being able to interview you on this. I think that we covered so many big ideas as well as a lot of really highly speculative ideas. But this is wonderful big picture material, and I'm honored that you joined me to discuss it. Let me close by asking what comes next for you, and do you see any big headlines coming soon in the nanotech world?
Well, I said I expected it in the next decade, and I'll stand by that. But I'm certainly not going to give you a year. As for what I'm doing right now, I'm building a robot. You see, there's his head, and there's his body, and I'm just having a lot of fun because I'm actually retired, and so I'm doing all the sort of stuff that retired people do, and saying, "Oh my God, I didn't realize how hard this really was."
Wonderful. Thank you again so much for your time today, sir.
All right, it's always a pleasure. Have a great day.